Recording is rolling. It is Tuesday, November 5th. Yesterday, you guys saw something. There's a new topic. We're talking about energy and conservation of energy. Eventually, we'll get to power, right? So, in time. And so, I do need to recap some new concepts with you guys. There's a new concept, there's a new framework of thinking, there's new equations, there's new units. Right. After I do a quick recap with you guys, I have some video demos. They're real short, so they encapsulate some stuff really nicely. And then you guys have on your desk a 3-page packet. It's a big old table. You guys see a big old table like this. It has a bunch of scenarios that you can solve using conservation of energy. So near the end of class today, here's what we're doing. We're building up towards this. I have lots and lots of posters I want to go over with you guys. Lots and lots of scenarios. There's a bunch I want to teach you guys. And like ideally, that's what I like to do. Right? It's just stand up here and lecture. But I want to build in an activity that's a bit more active on your part. So that's going to be that table. I'll show you guys how to solve some of those near the end of class today. And if I pace this out right, hopefully there's going to be like a solid 20 minutes at the end of class where you guys can just work on that packet, help each other out, work independently, ask me questions. I can walk around the room and help you guys out. All right, so here we go. Here's a recap. Here, guys, everybody focus here. Focus here. As soon as we go on. There's energy you guys learned about yesterday. So energy, in this class, we're going to quantify in, guys, what does J stand for? Joules, joule. And what is 1 joule? That breaks down into 1 Newton times 1 meter. So guys, if you push on something with some force for some distance, you're transferring energy into that object. By the way, the word for that is work, right? So capital W as a variable is work, right? It can also be in joules, so that's a transfer of energy. Right? So that's Newton times meters. And then that further breaks down into kilogram meter squared per second squared in terms of base SI units. Right. Now, we're not quite ready for power yet, but eventually, in the next week or two, you guys will see power, which is measured in watts, not to be confused with work. That's a different concept. Okay. So 1 watt is 1 joule per second. Okay, so I see what power is. It's a rate of energy. So if you have a light bulb that says 40 watts on it, it's drawing 40 joules per second. And that breaks down like this. All right, so we got new variables and units right there. Right. Now, energy can take lots of different forms. Do you guys think the amount of energy in a AA battery is finite? There's a certain amount of energy in a AA battery. There's a certain amount of energy in a gallon of gasoline. When you guys ate breakfast this morning, there was a certain amount of energy in your food. You probably quantified it in calories, like how many calories, but there's a conversion between calories and joules, right? There's, how about energy in a nuclear reaction, right? Now, guys, all those energy, guys, look up here, folks here. All those energies I just mentioned as examples are not on this page, because in this class, it's all of these puzzles that we're solving for the next couple of weeks. We're really focused on forms of mechanical energy, which is pretty much just this list right here. All right, so what do we care about? So work can be force times distance. If you push on something with some force for some distance, right? Or if you lift something for some height, I'll show you guys the graph that goes with that. All right, so you're going to see versions of this graph if you have force versus distance. Right? If you push on some, here I have a constant force for some distance. And then the area under that curve looks like a rectangle, right? And that represents how much work was done on the object. That's the amount of energy that was transferred. That's all, right? What if you have, okay, so you guys okay with that? What if the force is not constant? What if it's like any other crazy shape? Would the area under the curve still represent how much energy was transferred? Yeah, right. So in general, you can call it force times distance. Notice it's a dot product. The dot just means it's all in the same direction. So where's my example on that one? Right. If you lift something up some stairs, the vertical height change, it takes some energy to lift it, right? Right. But carrying it across the stairs, like this horizontal bit, that doesn't matter, right? How about pushing the shopping cart? Well, if you're pushing a shopping cart forward, only the forward component of your force is causing it to move in that direction forward, right? So the down part, like if you're pushing any bit down on the shopping cart, that doesn't move forward, so that doesn't matter. Right. So yeah. Right, so that's what the dot product means, right? And if you have this angle, guys, notice this angle. Let's talk about this angle. This angle is between those two vectors, right? So this force, this distance, this force, and this distance. You guys see angles between those two, right? It always ends up being a cosine, right? And you guys see a little bit different examples how it works out, right? What if you were given a little curveball question? What if they gave you this angle down here or this angle down here? This would no longer be a cosine. This would be a what? A sine, right? So you might see that version. So the definition, you usually see it set up with the cosine, but careful what angle you're given. There we go. All right, so it's a little extra there. What else we got? Well, if you lift something for some height, here's how much force it takes to lift is mg, and then the distance you live at, that's height h. That energy is now stored as potential energy, gravitational potential energy. If I lift this object up, say 1 meter, and set it at the edge of a table, now has that much potential energy. That's how much work it took to lift it and put it there in the first place. Okay. In this class, mostly focused on these gold rows, right? That's what I mostly care about. Right. Now, I have a couple of green rows. These are a little bit deeper. So if this gravity field is not constant, for example, if you send a rocket from Earth all the way to the moon, that G is not going to be constant. You do have to use this green box here. There's a lot I want to say about that, but I'll probably save that for a different day. Okay. All right. Then next one. What about compressing a spring? Guys, if I press the spring, does it take some force to press it? Yeah, in fact, it takes more and more and more force the more I press it, right? Oh, and I bet it took some energy too. Good thing I ate breakfast this morning, so I have enough energy in my finger right here to press this, the spring. How much energy are we talking about? Well, that goes back to this poster. Now, this is a poster from a long time ago. You guys see this orange banner, Hooke's law, F equals Kx. And notice, the more I press it, the more force it takes, right? And the more energy I'm also expending. How much energy we're talking about? This green triangle right here. You guys remember area under F versus X? Guys, it's the same set of axioms you guys just saw a moment ago. F versus X. Let me pull up that poster again. You guys see F versus X, right, in general? Here's F versus X as it applies to a spring, right? The area under the curve, which looks like a triangle shape, is still the amount of energy that was transferred into the spring, the amount of work it takes to compress it. Therefore, how much energy is in that spring right now? And it's also equal to the amount of energy I get back if I release it. It all comes back, maybe in a different form. Let's look at that. Let's look at that. All right, so x, kx, and then a triangle is 1/2 base height. Put it all together, you get 1/2 kx squared. You guys go with 1/2 kx squared is the energy stored in a spring. Okay, guys, do not confuse spring force with spring energy. A lot of students do that. That's a really common thing. I've been teaching this class many years. A lot of students mix these two formulas up. Guys, what is the force to compress a spring? What is that? Kx. What is the energy therefore stored in that spring? 1/2 kx squared. Okay, totally different concepts, different units. Newtons, joules. Okay. All right, what else we got? There's one last gold box, and that's energy of motion called kinetic energy, 1/2 mv squared. Here's a derivation. Okay, great. So suppose you're driving down the highway, and you know the mass of your car is like 1,000 kilograms, and you know you're going like 20 meters per second. I don't know, just whatever. Could you calculate the energy associated with keeping that car in motion? Yeah, just the fact that the car is in motion, right? Hey, could that tell you how much gasoline you had to burn to get the car up to speed in the first place? Yep, because that's where the energy came from, right? Because you can't create energy, you can't destroy energy, but you can transfer it to different forms, right? So it makes your car goes to gasoline, right? And that actually leads to this one right here. I just effectively mentioned this principle called conservation of energy. Right, so the sum of energy initial equals the sum of energy final. All the energy that exists in the universe today, the same as it was 1 billion years ago, same as it is 1 billion years in the future in terms of quantity, right? It's the same energy. So if you have a closed system, that means there's no external force acting on the system, so there's no energy transferred into or out of the system, so energy is conserved, right? Now, if you have what's called an open system, maybe there is an external force that's transferring energy into or out of the system. That's where I put the plus or minus work. Right? So you have some number of joules. If there's energy added or taken away from the system, right, then you have a different number of joules at the end. Okay, like that. Right. Now those joules didn't disappear from the universe; they just went into or out of the system, like that. All right. So we did some examples yesterday. Here's a real classic fundamental example. Galileo drops a ball, Leaning Tower. How fast does it crash into the ground? Right. Now, there was an old way of thinking of it with kinematic formulas, and we did this yesterday, and we got square root 2gh, right? So if you know the gravity field and the height of the tower, you can know how fast it crashes in the ground. Then we thought completely new framework. It's like, well, I know energy is conserved. Guess what type of energy at the top of the tower? Potential energy. That's mgh. What type of energy at the bottom of the tower? Kinetic energy, 1/2 mv squared. That's maybe a millimeter above the ground. So it's lost all its height, but it's moving really fast, right? Guys, is this energy equal to this energy? If this is 112 joules, is this 112 joules? Yep, that's why I can say equal. So this equals this. And then let's say you want to solve for V, you always get square root 2gh for dropping a ball off a tower. That's it. Real classic example right there. Here's this one's really similar. This one's not too different. If you throw a ball straight up, how high does it go based on your throwing speed? Or if you know how high does it go, can you say how fast did I throw it, which is right beneath the box right here. Right? Here's the old way of doing it with kinematic. Here's the new way of doing it with conservation of energy. These are completely different frameworks, but they lead to the exact same answers. Aha. One thing you'll see with these basic examples is like, okay, I have an old way to do it. I have a new way to do it. It took the same amount of paper, so it's about the same, right? Now, some of these puzzles, when we get going the next couple of weeks, you can solve a lot faster with energy. Maybe kinematic and dynamics is like, oh man, it takes like 3 pieces of paper. With energy, I can do it all on 1 page, right? And some puzzles, it's like, well, you can kind of only do it with energy, right? So in time. But for now, you're saying, oh yeah, that looks the same. Yeah. Ooh, I really like this example because it's pretty all encompassing. Like if I go back to my checklist, here's the main checklist today. The last 20 minutes of class, I'm going to throw this up on the board. Right? Is I've got gravitational potential, MGH. I got spring energy, 1/2 kx squared. I got energy of motion, 1/2 mv squared. Those are really the main 3 you're going to care about. Your main 3 building blocks to choose from, like an equation bank. Okay? And they're all right here on this poster. So recap this one. I take a mouse, I squash against the spring. Okay. Guys, how much work did it take to compress the spring? 1/2 kx squared. If I know what is k, this is the spring. I know x, how much I squashed it. Right. Then when I release it, pow! All that energy that came from the spring now goes into the object. Right. Now it has energy of motion, and now it's going up around the loop. Right, guys, to climb this hill, to climb this loop, what type of energy is that called? Gravitational potential. There's your MGH. Right? And to make it around the loop, it better have some speed up here, right? Otherwise, it's going to fall off the track. Right. And what energy is associated with the speed? Kinetic, and that's called 1/2 mv squared. Let's do a numerical example. Suppose you squash the spring. I get like 100 joules. I'm just making up something. 100 joules. Suppose it took 30 joules to lift it to this height. How many joules of kinetic does it have? Guys, if this is 100 joules and this is 30 joules, how many joules go here? 70, right? Furthermore, if I told you what the mass is, especially like the mass is like 100 grams or something, right? Could you calculate the speed it has at the top of the loop? Yep, because you say this. Oh, I know this must be 70 joules. So if mass is such and such, I can solve for V. You guys can do that, right? So this is the new thought process, right? You guys good so far? All right. So I have we're gonna save this one for later. Did that right? So this is the last poster you guys saw yesterday, and I'm about to play some demos. Let's walk through this one a little bit. Right. So, it got a roller coaster. It's got a hill, feeds into this vertical loop. And I know if I want to make it around the vertical loop, there is a minimum speed to get around. And that's this box right here. This is something from a couple of weeks ago. It's the same as the water in the cup. You guys remember that? Water cup, vertical loop, right? V minimum is square root GR, right? It's got to go at least that fast to make it around, right? Now, the extension question is going to be, well, how tall does this hill have to be so that it reaches that speed so that it makes it around, right? You guys got that, right? And that you can solve with this conservation of energy. So let's go through this right here. We'll do this right here. Here, we'll do 1 step at a time. And so energy is conserved. Guys, what type of energy at the very top of the hill? Potential energy, MGH. Okay. Now, I do have to define a floor, like where's ground level. I'm going to define the floor, the ground, exactly where my pen is. You guys see where my pen is? Way down here, right? Could I define the floor wherever I want to? Yeah, right. If I want to be crazy, could I define the floor here if I wanted to? Yeah. Could I define the floor here if I wanted to? Yeah. Could I define the floor up here if I wanted to? Yeah. Right. Now, if I did that, suppose I put the floor like right here. Does would the block go into negative height at some point, like a negative height? I could treat that as a negative energy term, right? I could do that, right? Do you think I would still get the correct answer at the end? Yeah, I would, as long as I keep the floor consistent, right? I'm going to put the floor down here. I think that's probably the best place to put it. You guys think? Right. So here's the total hill height, and you guys said it's all MGH up here, right? Now, by the time the cart gets to this point, the top of the loop, that's what my point B. I'm going from point A to point B, initial to final. Does it have some height it had to climb to get up to that point? Yeah, equal to 2r, right? Twice the radius of the loop, right? And it better have some speed left over because it's got to make it around. In fact, it has to be moving at least this fast, right? So is that potential and kinetic? Right? If you set up an equation, you guys are going to do some of these later. This is what this looks like at this point. MGH here is exactly equal to the energy here, which is mg2r plus another 1/2 mv squared. Right? Now, if you go step by step by step, here, let's do the next step. Because this v squared has to be at least how much? GR. And you know that from 2 weeks ago. So I'm going to substitute that, right? Then combine some terms. Because at this point, okay, so I'm down to that line now. What variables cancel out on both sides? What's one variable that cancels? Mass. Yeah. So see if you guys can follow. What does that mean? If you have an empty cart and it makes it around, and then you have a cart full of people, which is a lot more massive, would you still need the same minimum height hill? Yeah. Yeah, because the mass is about to cancel out, which I have covered up here. That's going to happen. What variable also cancels out? Gravity field. So whatever the answer is that I have covered up. Suppose I take this to the moon and then I take this to Mars. Would I still need the same hill height to guarantee that it gets around? Yeah. Now I do need gravity to make it fall. Oh, but it's just going to float there if there's no gravity, right? But once there's a gravity field, it does not matter how strong the gravity field is because I have 1, 2, 3 terms here. You see 1, 2, 3 terms, and they all have the M and they all have the G. So the M and the G both cancel. Okay. It doesn't matter if it's empty or full of people. It doesn't matter if it's on the Earth, Moon, or the Mars, or the Earth, the Moon, or Mars. The Mars, whatever, because it's the Mars now. So if you solve for H, that's the question. What is the minimum height? I'm solving for H, right? Can you guys do the algebra and solve for H? Here, I'll show you guys the answer. Because this is a really classic physics question. If you take physics in college, you're going to get this question, and I'm giving you guys the answer right now. The answer is always what you're looking at right there. Let's do a numerical example. Suppose the radius of this loop is like 10 meters. You guys got that? What is the diameter of the loop equal to? Guys, if this is 10 meters, what is this? 20 meters. Right? This is 10 meters, this is 20 meters, right? And therefore, what is the minimum height of the hill? If you put a 10 meters right here, what's 10 divided by 2? It's 5 times 5 is 25 meters. 25 meters, right? As long as my hill is at least 25 meters tall, right? And ideally, maybe you want taller than that. But if it's any shorter, if it's like 22 meters, forget it. These people are going to, they're going to fall off the loop, right? If it's exactly 25 meters tall and there's zero friction, that is barely squeak around. Okay, let's do that. All right. So, like I said, I have many good posters after this that I would love to just sit here and talk about for like 4 hours, but we're gonna do a little switch here. So it's demo time.